In this video, we will do an example where we count the number of card hands with a certain property. So the example says that a standard deck of cards has 4 suits, diamonds, hearts, spades, and clubs, each with 13 cards. So each of them has an A, which stands for ace, the integers 2 through 10, so they have 2, 3, 4, all the way up until 10, and then 3 other cards called a jack, a queen, and a king, which I'm labeling as J, Q, and K. How many 9-card hands will have exactly 4 hearts and 3 diamonds? So by 9-card hands, it means that we're going to be selecting 9 cards from this deck of cards. All right, so the first thing that I want to point out is, in this example, the order does not matter. The order in which I'm selecting our 9 cards to go in our hand does not matter. So let's think about what our strategy would be. So our strategy. But noticing the fact that the order does not matter makes us think of combinations rather than permutations. So overall in this problem, we're going to have to pick 4 hearts. We're going to have to pick 3 diamonds. So let's think about those first. So we're going to have to choose 4 hearts. That's definitely something we're going to have to do. We are going to have to choose 3 diamonds. And then to complete our 9-card hand, we still would need 2 more cards, because 4 hearts and 3 diamonds, that's 7 total cards. So then we still need to choose 2 non-heart / diamonds. So these are either going to be clubs or spades. All right, so let's think about how many ways there are going to be to choose each item here. So let's do the 4 hearts first. So we need to select 4 hearts, and there are 13 total hearts in the deck of cards, because each one of the suits has 13 cards. And the order in which we pick those 4 hearts does not matter. So we're going to use combinations. So I'm going to use my notation for combinations. So I'm going to use this narrow parentheses notation, and I'll put a 13 at the top, because that's how many total hearts there are. And we need to choose 4 of them. Okay, so the way I read this in words is this is 13 choose 4, and it's notation for combinations. So 13 choose 4 ways. So a little bit later, we'll remind ourselves, well, how do we figure out what this is, what 13 choose 4 is? But for right now, let me just keep it at that. Let's move on to diamonds. So for diamonds, okay, well, there's 13 total diamonds still, but we only need to choose 3 of them. And the order in which we choose them does not matter. So we're going to use combinations. So 13 total diamonds, we are going to choose 3 of them. So I put this narrow parentheses around it. So we're going to have 13 choose 3 ways. That's how I read it out loud. I say 13 choose 3 ways. And then finally, I got to think about, okay, choosing these 2 non-heart diamonds. And again, the order in which I choose them does not matter. So I'm going to use a combination, narrow parentheses. So how many cards are there that are not hearts and not diamonds? In other words, how many cards are there that are either clubs or spades? Well, there are 26 clubs or spades, because there's 13 of each. There's 13 clubs, there's 13 spades. So if I want to count how many there are overall clubs or spades, I add 13 plus 13 to get 26. So I'm picking from a pool of 26 cards that are clubs or spades, but I only need to choose 2 of them. So I'll have 26 choose 2. All right, so we are ready to write down our answer, at least in terms of our notation. So we had for the, for the hearts, we had 13 choose 4 ways. We'll have to work out what that is. For the diamonds, we had 13 choose 3 ways. And then for the 2 cards that are not hearts or diamonds, whoa, sorry about that. Screen keeps getting shifted here. Keeps happening. Sorry about that. Hold on. Let's see if I can get this. All right, so we have 26 choose 2 ways for those others. Okay, so I'm going to go through how we figure out 13 choose 4 slowly, but then the others I'm going to do a little bit more quickly. So for 13 choose 4, we're choosing 4 objects from a set of 13 where the order doesn't matter. So I'm going to start off as we usually do. For the first object, there's 13 choices for what we could pick. And then once we pick that first object, now there's 12 choices left for the second object. And then for the third object, after I pick the first 2, there's 11 choices left. And then for the fourth object, after I pick the first 3, there are 10 choices left. But of course, that's what we would do for a permutation, where the order matters. Because the order doesn't matter, I need to adjust for overcounting, and I got to divide by the number of ways to rearrange 4 objects once I've chosen them. And the number of ways to rearrange 4 objects is 4 factorial, and that's what I divide by. And you might remember from the previous videos, this was also one of our formulas for the number of combinations. So this is just what I'm saying 13 choose 4 is. 13 choose 4 is this fraction. So if I do the same type of thing for these other fractions, for 13 choose 3, we'd get, whoops, I don't know what it is about this video. My screen keeps getting shifted. 13, whoops, 13. 13, and then for the next object, 12 choices. And then after I pick those 2, 11 choices for the next one. And we stop there because we're just picking 3 objects. And we got to adjust for overcounting, so I divide by 3 factorial. Okay, because that's the number of ways to rearrange those 3 chosen objects. And okay, so that is what 13 choose 3 is. And then finally, let's do 26 choose 2. So that will give me 26 choices for the first object, and then 25 choices for the second one, and then we divide by the number of ways to permute 2 objects, which is 2 factorial. All right, so 26 choose 2 is this last fraction. And if we multiply out these numbers, we will end up with 66,459,250. So a really big number, but that is the answer to our question. So I want to end this video with a quick note about the other formula for combinations involving factorials. So the other formula for n choose k, that's how I say this notation, gives, I'm going to do it for one of these combinations. Let's do it for 13 choose 4. If I use the factorial formula, we would get 13 factorial over 4 factorial times 13 minus 4 factorial. So if we simplify this, we get, if I write out 13 factorial a little bit on the top, this is 13 times 12 times 11 times 10 times 9 times ... until I get down to 1. And then on the denominator, I have 4 factorial times 9 factorial. But I notice something really nice happens. The 9 factorial can cancel with all of these terms at the end. I could have also canceled the 4 factorial with some of the terms at the end, but the 9 factorial is going to cancel with more of them, and that's why I decided to cancel the 9 factorial. And that'll leave me with 13 times 12 times 11 times 10 on top, 4 factorial on the bottom, and notice that that is the same as what we had gotten above, just thinking about it logically, how we did with our first formula for combinations. So let me write that down, which is the same as above. So in the next video, we will do another example that involves committees with a president and a vice president and some general members.